Okay, so this is the third lecture of EE 225B. We have had a bit of a rough start, as you all know. We started on 12:30 to 2 on Wednesday. Then people brought to my attention that the class was online schedule, and all the schedules were reflecting it was still at 9:30 to 11. So to stick to the online schedule, we switched to 9:30 to 11. But for the second lecture, which was on Friday, we couldn't get an operator. So finally, we resolved all of those, and today we're meeting at the correct time with an operator that will videotape the lecture. Just a quick show of hand, how many people were both in the first and second lecture? Okay. How many people missed at least one? Okay. So the lecture notes, lecture number 2 was primarily a review of DSP. It wasn't too critical. The lecture notes for it are online. Unfortunately, that's the one lecture you can't watch the video because we didn't have the operator. I hope that I've tried everything I could with mass emails and various other things to let everyone know about the time change.
I think you've turned off the mic. I had it turned on as you said.
It says, oh, you mean from mute go to on? Okay, that's quite possible. Is it on now? Okay. So one other announcement I'd like to make is Cindy's office hours are now Tuesdays and Thursdays from 3:30 to 5. Cindy Lou is the TA for this course. And the room for her office hours are Corey 479, right? Okay. Cindy Lou office hours Tuesday, Thursday, 3:30 to 5, 479 Corey. And my office hours are immediately after the lecture on Friday. It's Fridays 11 to 12. They're all on the website. Okay. And is there anybody who didn't attend either the Wednesday or the Friday lecture of last week? No. Okay. So we have a kind of a combination of so some people must have missed one or the other lecture. I checked with ASUC or with the department person who deals with the books just this morning. They claim the delay is from the publisher side and not from them, and they think they're going to get it by the end of January. So if you're anxious, if I assign any homeworks at this point, I'll make sure that chapter 1 of Jay Lynn's book is on the web page so that you can read it so you can do the homework. Did you change the thing to 2 hours? The book on the reserve?
Right now we have the Jane book reserved in the library, but there's only one copy and it's reserved for 2 hours. Okay.
So if push comes to shove, and the book just doesn't arrive in the next 2 or 3 days, one thing I might do is there's 2 solutions. One solution is we'll scan chapter 1 of Jay Lynn, put it on the web so you can do you can have the reading material to do the first homework. That's option 1. Option 2, if you can, order it from Amazon. Option 3, we'll put it on, it is already on reserve, so each one of you goes to the library, and I would dare to say it takes 15 minutes to copy the first chapter. There's a Xerox machine there, at least last time I was there. So you can just copy the first chapter, just so that we can get going with the first homework. I don't want the homeworks to get piled up at the end of the semester. Students always hate that. I hate that, you hate it, everybody hates it. So just to get the course rolling, that's one thing we might want to do. Has anybody got a copy of this book? I could, there's copyright issues. I could go to jail for doing that. Because, I mean, you certainly don't want your instructor to go to jail. You also don't want your instructor to die either. Those are 2 bad things. Because just, if everybody put chapters of books on the web, then the authors, in fact, it just so happens this is my old professor, so that's even more reason not to do it. But we have put, last year, because the book was delayed, we did put the problems for the first problem set on the web, and that's already on the web of the spring 2003, but I've never really dared to just get a copy of a whole kind of chapter and put it on the web. But let me see. Let me just wait one or two more days. At this point, I haven't covered enough material to even initiate the homework, so it's still not a big deal. But at the end of today's lecture, we'll have enough to do that. So I'll discuss it with Cindy. I think putting it on the web is you're right. It's probably. Well, here's what we might do: is we might put it on the web, and in fact, let's do that. Okay. We'll put it on the web for a very short time. Let's say just Friday. She'll put it on the web just before at 9 a.m. Can you do that, Cindy? 9 a.m. on Friday. And we'll knock it out so we don't get caught by, what do you say? How about if we do it by 4 p.m.? Will that give you guys enough window? Just go there, print, and you're done. Yeah? Does that work with everyone? Yeah, Cindy? Okay. So I'll give you a copy of my book, and let me just make sure that it is chapter 1 and not 2. Yeah. Yeah, wow. I was going to say it's only a few pages. It's 64 pages. So you have yeah. Yeah, we'll arrange between you and I and Rosita how do we do that. So I'm not going to write this announcement on the board because there'll be yet another evidence of our misdoing here. But so chapter 1 will be on the web on Friday from 9 to 4. So please print it and have a copy of it until the book arrives. Okay, that's all the administrative stuff. So let me get started on the real lecture today. Today, what we're going to talk about is tomography. Yeah, sure. Can you use the mic, please? That's okay.
Yeah, just in this simple 1D convolution case I was going over, we were talking about the number of operations that are required to do a convolution. If there's like M samples and H and N samples and F.
Right.
Can we go over that just one more time? I wasn't sure if it was like N squared times M or N times M per convolution.
I didn't bring last time's lecture with me.
Okay.
Can we do that?
I
at the end of the lecture,
class or something.
Yeah, let's do that. So the gist of it, I have this lecture notes here. The gist of it is that if you have separable filter, the signal that you receive, a two-dimensional image that you receive, you don't have much control whether it's separable or not. It's a picture of something, somebody, etc. You got to process it no matter what it is. But the filter is what you can make separable. And if you use a separable filter, then the number of operations grows as 2mn squared. Let me write that down. And there was one other person who asked the same question, which means that I was probably not all that clear on it. So this is the number of ops if the filter, is separable. And m by m in this case is the size of the filter, right? And n by n is the size of the image. On the other hand, if you design your filter not to be separable, so if filter is not separable, then we get m squared, n squared. Okay, so the ratio between this and this is m over 2. So if you're not separable, you're m over 2 times more complex to implement than if you are separable. So if m, for example, is 10, then this is 5 times more complex to implement. Is that what you were asking?
Yeah, that's
okay. I think in the heat of trying to arrive at these expressions, I might have not painted the big picture, which is if you design your filters to be separable, you gain in computation. You lower the computational complexity by a factor that's m squared. And when I say ops, I mean mults or adds. Okay. Okay, any other questions or comments? Okay, so what I'm going to talk today is tomography application. So tomography is used in quite a bit in medicine, right? When you have a CT scan, a CAT scan, the principles of tomography are used all the time to detect tumors and various other things. They're also used initially when they were designed. They were the systems are very slow because of the computational aspects of it. But now you can have a cinematic reconstruction of a beating heart, for example. Okay, you can use X-rays, you can use gamma rays or positrons or all kinds of particles to do tomography. It also has applications in acoustic or microwave transmission. It is also used in geologic measurements from boreholes. So, for example, oil companies, one technique they do is they drill a hole here, drill another hole there. They put transmitters and receivers, and they send a microwave signal that, and they change the height of the transmitter and the receiver at the two ends. I'll draw a picture of it. And by sending a signal and receiving it at different heights, it's almost like a projection, and they can reconstruct the layers of Earth. And by looking at the layers of Earth, they can figure out, the likelihood of finding oil in this spot or not. One of the biggest costs in oil exploration is that of approximately every 10 times that they dig a big hole and invest a lot of money, only once they actually find oil. So being able to come up with advanced signal processing techniques to increase that probability is a big deal. And again, over the last 18 years, I've passed this course, depending upon what era we're in. Sometimes oil is expensive and beer, and sometimes it's dirt cheap, and now we happen to be in a period where it's expensive. When I had just graduated from MIT looking for a job, I interviewed with other oil companies like Chevron and others, and like the executive would say, what we really need is a good, big, healthy appetite for oil. And at that time, the price of oil was very low. And of course, now it's very high. So the other applications of tomography are electron microscopes. You're looking at specimens, and you shoot electrons, and what you receive is a projection of the specimen. You can reconstruct the specimen using tomography techniques. So radio telescopes, when you're looking at the stars, projections of interstellar space, and various other systems. So let me just show some picture and define. So an integral part of tomography is really the concept of projection. So let me define what a projection is and draw some diagrams so that we can get going with the mathematical definitions of it. Okay. So if you can bring the camera down, please. So tomography is what we're covering today. Suppose that I have some sort of an object here. In general, you talk about, let me lower this so I can see this half of the class. In general, thank you, you have a three-dimensional object, and then you have a source, let's say an X-ray, and then you compute the two-dimensional projection of the three-dimensional object. For the purpose of today's lecture, we're going to talk about two-dimensional objects. Think about an object that has a two-dimensional function, essentially. And we take a projection of it. Let's say we put the X-ray here, and we get a one-dimensional projection, just so that I can draw it easier on paper. But in real life, like if you're having a CT of your body, your body is a three-dimensional thing, and the projections are in 2D. So what do I mean by projection? So let's say you have an object here, and you put an X-ray source right here, and you want to take and let's say the object has two bumps. So there's like two tumors or something like that. One thing is here, and another one is here. Then you can take the projection of this, along this direction. Which is really, if you think of it as a two-dimensional function, it's really the integral of that function along these paths, and it gives me just a one-dimensional function that could look something like this. And then I move my X-ray source here, and then I take another set of projections, which is the integral of the two-dimensional objects along that axis, and I get another one-dimensional function here. So by moving the X-ray source around the object, then you can obtain projections of the two-dimensional objects along different angles. So this is projection number 1, this is projection number 2, this is projection, and so if I put the X-ray source now next here, then and the integration is done that way, and I can get a third projection, which is another function right there. Okay. In real life, you don't necessarily want to rotate an X-ray machine that's so big and complicated around a patient. Rather, you rotate the patient in order to get the different projections. So that's one of the differences. But the key thing here is, what is the definition of a projection? Well, projection, in mathematical language, is just an integral, and we'll write that down in just a second. But it's a mathematical operation that's similar to the physical operation of taking an X-ray photograph with a collimated beam of radiation. So let me write that down. So here's the definition of a projection. It's a mathematical operation that is similar to the physical operation of taking an X-ray photograph. With a collimated beam of radiation. And because I'm not the best artist, I'm going to show a picture out of this book, Dungeon and Mercer, which is a pretty old book, but it has a really nice drawing that I'd like to flash on the screen for just a second. Just to show you, if you can zoom in into this picture, that would be great. So suppose, again, this is not a patient, but it's an object. Suppose you have an object with this kind of a density. It has 3 holes kind of in the middle of it. Some metal that, due to erosion or some other bad thing, some holes have appeared in it, and you want to detect it. So if I put an X-ray source here and project along this direction, you get a function that, as it hits these holes, it has a dip here, and then another dip here, and another dip here. So by looking at the projection, you might be able to you might be able to detect something is going on. And then after you detect the first projection and you suspect something is wrong, you say, we've got to do more projections because this plane could have a crack, or this object could be defective, and you can take more projections to find out. In general, projections are expensive and time-consuming. So sometimes the goal is to collect a bunch of projections and then reconstruct this two-dimensional function here. That's very costly. If you want to represent this function very accurately, you have to take lots and lots of projections, sometimes 64, 128, or a ton of them, and that could be very timely. But if the first projection already shows there's reason to take more, then you do it. Kind of like medical procedures. You have one test, so, well, this thing doesn't really look good, let's dig in, have another test, etc., etc. Okay, so as I said, I'm going to draw yet another picture, or show another picture from this book for the geology application, because I think it's a nice example if you can zoom in again. Okay, this is the use of boreholes to acquire information about the geologic formations using acoustic beams. you basically, down in the borehole, you put an acoustic or microwave transmitter. This is the transmitter. H sub t is the height of the transmitter. And you transmit a signal, and there's some two-dimensional density here that you're trying to reconstruct. And you have a receiver, and you put as this is transmitting, you put the receiver here, you put the receiver here at different heights. You collect the signal, and then you also vary the height of the transmitter, and that way you're computing the projection of you're assuming, fundamentally, you're assuming that the only signal that's received propagates in a straight line from the transmitter, which is a fairly good assumption in many cases. And then once you've achieved the projections, you want to come up with the reconstruction of this region, which could be useful for mapping hydrocarbon deposits, essentially oil exploration. Okay, so let's get into the mathematics of it just a little bit more. I'm going to draw another picture here, a little bit with more with more labels on the axis, etc. So suppose this is our two-dimensional object that we're interested in reconstructing. And I put these axes T1 and T2, okay? And suppose that I'm projecting at an angle that's theta, that makes an angle theta with this axis here. So this is my new axis U, and when I do that projection, so there's a bunch of, let me use a different color here. So there's a bunch of lines. So there's essentially line integral happening along each one of these lines, and what I receive at this end, and again I will use a different color, should I use this earlier? So this is my U-axis, and this is my perpendicular to the U-axis is the T-axis. This is T1, that's T2. Let me put 1 here, okay? So after I do the projection, I get some sort of a function going up and down here. Okay, this blue is the projection that I've achieved, and this axis again, this T makes an axis theta, makes an angle theta with this line here, which is parallel to T1. Okay, so after I compute the line integral of this two-dimensional object along this direction, this function here is called, we refer to it as P sub theta of T. Okay, what is the function of T? For every value of T, it has a value, and this is called the projection of this function here, this two-dimensional function. This guy, we refer to it as F sub C of T1 and T2. Okay, we're assuming it's a continuous signal, a continuous space signal in 2D. Okay, and this P sub theta of T is the projection of it. So it's the projection of F sub C of T1 and T2. Okay, so the first question that you ask yourself is, what is the mathematical? Can I write down an expression relating this P sub theta of T, this new function, one-dimensional function, to this two-dimensional function, Fc of T1 and T2? Think of Fc as something that's sticking out of the paper. It's like a mountain. You know, for some values of T1 and T2 is high, so for some it is low, and its extent is kind of shown by here. Okay, so so mathematically, what do I mean by projection? I just tell you it's a mathematical operation that corresponds to the physical operation that the X-ray does, but what is that mathematical operation? So let me start by writing that down, and then my next objective is to show what's called the projection slice theorem, which relates the two-dimensional Fourier transform of this two-dimensional signal to the one-dimensional Fourier transform of this signal. So to begin with, here's the definition of projection. P sub theta of T, the projection, is the integral, and you can kind of see that as I write it. I'm integrating along the U dimension. So it's an integral for U going from minus infinity to plus infinity of f sub c of t1 comma t2, where, so this is a long du, where, how do I get rid of t1 and t2s? Well, the left-hand side only has t's. Well, t1 is related to u and t, right? T1 and T2 are at an angle theta with UT line. So T1 is nothing but T cosine theta minus U sine theta, and T2 is nothing but T sine theta plus U cosine theta. Okay, so mathematically speaking, for this picture up here, this is the equation that relates this one-dimensional projection along the angle theta, along the axis u, which makes an angle theta for this, to the original two-dimensional function f sub c that we had up there. So this is the projection. Okay. And what I'm going to show in the next 10, 15, 20 minutes is, as I said, relating the Fourier transform, the two-dimensional Fourier transform of this guy to the one-dimensional Fourier transform here. So let's dive into that process, hopefully without getting too bogged down in equations and details. So the goal, to write it down, is relate the 2D Fourier transform of Fc to 1D, D stands for dimension, Fourier transform of P sub theta. Okay? And this is done using projection slice theorem, and I'll set it up, and the actual derivation will be part of your homework. It's pretty straightforward, and it merely involves change of coordinates. But just so that to help you do the homework, let's just do the setup. So I want to state, and this goal is achieved by what's called projection slice theorem. And this has been in existence for many, many years. And it's been reincarnated in signal processing and various other fields over and over again. But to get going on that, let's write down the two-dimensional Fourier transform of f sub c here. Okay, what can we say about the 2D Fourier transform of f sub c? Well, f sub c is a two-dimensional function of continuous t1 and t2, or continuous space. So you just plug in the standard Fourier transform formula. Omega 1 and omega 2 are the frequency variables in 2D. So this is a two-dimensional continuous time Fourier transform of f sub c of t1 and t2. Okay, which is then given by what's the expression for it? T1 ranging from minus infinity to plus infinity, T2 ranging from minus infinity to plus infinity of f sub c of t1 comma t2 e to the minus j omega 1 t1 e to the minus j omega 2 t2. And these omega 1 and omega 2s are also continuous variables in the frequency domain. And we also know the inverse Fourier transform. We also can obtain, so this is still fc of omega 1 and omega 2. This is the Fourier transform of little fc. We can also obtain the little fc, the space domain signal, from its Fourier transform using the following mathematical equation. Fc of t1 and t2 is given by 1 over 4 pi squared, which is merely a scaling factor, and then double integral of fc of omega 1 and omega 2, e to the j omega 1 t1, e to the j omega 2 t2, d omega 1, d omega 2. Okay. And now what we have, I'm going to open this sheet. So some of the things we do with paper under the camera is things that you really cannot ever do on the board. That you can't fold the board and move it around. Okay, so this is the expression for forward Fourier transform. This is the expression for inverse Fourier transform. And way up here, if you can roll up just a tiny bit, yeah, this is the projection relating the two-dimensional function to the projection function. So because I want to relate this 2D Fourier transform to the one-dimensional Fourier transform of this guy, so let's write down the expression for one-dimensional Fourier transform of p theta, and what is that? Well, I'm going to denote it with p theta of omega, where this p is supposedly capital and this p is supposedly small, but usually from the variable inside, you know this is the Fourier domain and this is the time domain. So this is the one-dimensional continuous time Fourier transform of p theta of t. So therefore, this capital P theta of omega mathematically is written as the P theta of t times e to the minus j omega t dt, where t goes from minus infinity to plus infinity. This is again straightforward definition of Fourier transform. So it's all, so far I've only written down definitions. And what projection slice theorem tells you is that it relates this Fourier transform, this one-dimensional Fourier transform of this blue signal, to the two-dimensional Fourier transform of this black signal. So it relates essentially this expression to this expression here. And what it says is this, projection slice theorem. It says that p theta of omega, the one-dimensional Fourier transform, is just a slice of the two-dimensional Fourier transform. That means it's just f sub c of omega 1 and omega 2 evaluated at this slice. And the slice is omega 1 is equal to omega cosine theta, and omega 2 is omega sine theta. And pictorially, so which means this is equal to fc of omega cos theta, comma, omega sine theta. So pictorially, what does all this gibberish or mathematical stuff mean? Well, this is what it means. This is p theta of omega. It means that if I were to draw in the omega 1, omega 2 plane, this is my fc of omega 1 and omega 2. Then if I go to a particular angle theta and take a slice of that, so imagine this red blah as a two-dimensional function sticking out of the board. Imagine like a birthday cake or something sticking out. So if I take a knife cutting the birthday cake and I go and evaluate the function along each point here, I get a one-dimensional function. And that one-dimensional function is p theta of omega. It's a slice of this two-dimensional function along this. Okay? So this is nothing but p theta of omega. So that's a pretty, does everybody follow this analogy that we just made? Okay. So that's a pretty powerful theorem because, and again, it's pretty straightforward to show this because what does it mean? Well, it means that if I took the projection along this angle, I get a slice along this. Then if I change the angle and get another projection, I get a slice along here. Then here, 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 here. Pretty soon, I get enough slices. I almost have the 2D Fourier transform of the object I'm after. And then at that point, all I have to do is the 2D inverse Fourier transform to get the object itself. And the object itself is the thing we're interested in. You know, how many tumors have I got in my breast, or how many tumors in my brain, or things like that. Hopefully we'll never get any of those, but that's the information you're after. The two-dimensional object to begin with. Okay? So the main idea is by taking multiple projections, then you can get a pretty good idea of the 2D Fourier transform of the object. And then you do an inverse Fourier transform, inverse 2D Fourier transform, and you get the object, which in this case, in our case, is f sub c of t1 and t2, this is what we were after. and so in real life, actually, in fact, we have one professor in our department, Bernard Boser, who probably some of you don't know because he's currently on sabbatical leave in Switzerland. He actually worked on, let's see, A to D sampling techniques for X-ray tomography applications with some guys at UCSF. So essentially, when you do in real life, when you want to take a projection, and when you're doing X-ray, you put A to D samplers here it's very hard to compute or to get the continuous function. You get samples of this guy, and then once you have samples of this guy, then you can take the discrete Fourier transform of that, and you get samples in the Fourier domain. Okay. Are there any questions so far regarding this setup before I go into more details?
Yeah, I was just curious, I guess, how the sampling works. So your samples are really samples of beta, right? And so you get a bunch of slices.
Right.
So, I don't know.
How do you get the signal? I'll explain. That's kind of the next 40 minutes of the lecture.
Okay.
You're wondering from these, how do you get the signal?
Yeah.
Yeah, it's coming. It's coming. Right. All right. Oh, yeah. I'm going to dive into that, but so far I just wanted to make sure that this concept is clear. Okay, so what happens is now, as a result of taking your projections, you end up with, let's say you took a number of projections, and 1, 2, 3, 4, 5, 6, 7, 8. Yeah, in the example I'm going to show, suppose that you took 8 projections, and for each one of these projections, you managed to get 8 equally spaced samples in the Fourier domain. So in the omega 1 and omega 2, suppose you take the endpoint DFT of the projections. And let me just say, for my example, what M is 1, 2, 3, 4, 5, 6, 7, 8, 9. So suppose I take a 9 equally spaced samples. So if my angle was theta, I get 9 equally spaced points here. 1, 2, 3, 4, 5, and 6, 7, 8, 9. And then I get 9 more along this direction. And yeah. So basically, I'm going to cheat here, and basically what it is I get pretend I didn't do that. I'm only doing that so that I can have my samples in the right place. Okay? Okay. So suppose I get these after I take the M point, in this case M is 9, so I have 8 projections, and this is 1, 2, 3, 4, 5, 6, 7, and 8, right? And suppose when I take the endpoint DFT of it, you can easily show that if the spacing between these 2 samples is the same as between these 2 samples as between these 2 samples, okay? These are my samples. Right. So if the spacing between the samples for each projections are the same, constant, or don't change from one projection to the other, I end up sampling what's called in a polar fashion. So this is called polar sampling of my 2D Fourier domain. Okay. So in polar sampling, every angle essentially uses an endpoint DFT. Every angle, the spacing between the samples in the Fourier domain are equal. Okay? And so how would, from these polar samples, which I've now put them in red, how can we compute the 2D Fourier transform of the original object? Well, the 2D Fourier transform of the object, let's say we wanted to compute this thing over 16 samples. They're more on a rectangular kind of grid, right? And so they would be like here, 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 here. The blue guys, right? So one question that oh, I know what I did wrong. I have 4 on this side, and no, that's correct. No, that's fine. It's correct. I have 4 on both sides. That's good.
You get 9 samples per angle and that's not angle.
Yeah, something like that. So the question is, I've got the red dots, or the red crosses. How do I get the blue ones from there? Anybody has any ideas? While I fill out this painful plane. How would you do that? How about something very simple? You have the samples in a polar plane, and you want to get the on a rectangular or Cartesian grid. How would you do it? Interpolation. How would you interpolate? What would be one easy method of interpolation? There are many kinds of interpolation, right? You can do sync interpolation. What else can you do that's simpler than sync, for example? You can do average, so linear interpolation. So, for example, you could say to compute this point, I'm going to look at a fixed radius of samples around it, and I'm going to have a weighted average of the samples around it, where the samples that are closer, I'm going to give more weight, and the samples that are further away are farther away. That's called linear interpolation. In fact, it's called first order interpolation. What's the zeroth order interpolation? It's very simple. I'm sure you... Exactly, nearest neighbor. So I can just say, okay, so for this point, this is the closest sample. For this point, this is the closest sample. So basically, to get the bottom line is, let me move on to the new page, is to get the blue samples, blue Cartesian samples, from the red polar samples, in this case, I need to do some sort of interpolation. And I can do zeroth order interpolation, which means that it's called nearest neighbor, and that's used all the time in lots of applications. I can do first order interpolation, which is the weighted sum of neighboring samples, or weighted average, rather. Okay. So those are 2 popular techniques people use, and then I'll show you the results from this in just 1 second if you apply it to some real life signal and all that. But before doing that, I want to talk about a different possibility, and that is, in this case, we assume that the distance between the red samples for this projection and the red samples between these projections are all the same. That's why we got a polar kind of a distribution. Now, if you change the distance between these samples as a function of the angle, the red dots will no longer be on polar circles, but there will be on concentric squares. So let me, and it would look something like this. If you could zoom in, please. Okay. So this is what you get, as you can see, the distance between successive samples on this projection is the same as the distance between successive samples in this projection. Now, if you change that, you get something like this. So along this projection, this diagonal one, for example, the distance is longer between successive samples. They're all the distance between the samples are all equal for every projection, but that equal space here is different from that equal space here. So this projection, for example, has the samples closer. So essentially, you've changed the sampling rate as a function of the projection angle. And then you get this kind of a thing. And this is called concentric squares. And there's nothing wrong with that. You can now either use, again, either nearest neighbor or first-order interpolation in order to estimate the values of equally spaced values of the two-dimensional Fourier transform, which will then allow you to take inverse Fourier transform to get the samples. So coming back here, let me write it down. So you can have concentric squares where the distance between the projection samples in Fourier domain varies as a function of projection angle. Okay, and then you get concentric squares. So let me just, with these two very simple, I'm going to talk about a little bit more fancier reconstruction techniques, i.e. the radon inversion formula and the iterative technique in just a second. But for now, let me just show you some results for the simple-minded nearest neighbor and first-order interpolation. So what we have here, this is again off of Dungeon and Mercerot. Actually, zoom out just a tiny bit so all four can be shown. Great, thank you. So what we have here in the upper left is a original signal our goal is to reconstruct. It has a lot of good details. It's got a lot of angular details, and it has a small circle here and a big circle here. So lots of good things to try to reconstruct. And what's shown here is if you use 64 projections, 64 equally angled projections, and using the polar sampling and also zeroth order, which means nearest neighbor reconstruction. And this is again polar, but using the first-order interpolation. Clearly, first-order interpolation results in better reconstruction than zeroth-order interpolation. So this, you're doing weighted sum or weighted averaging of the samples that are around you. Here, you're just saying, give me the closest sample, and that's it. So this does better than that. And this is if you use linear interpolation and use concentric square kind of a sampling of the Fourier domain. And you could argue whether this is better than this. I would say this has a slightly better contrast than this, but it also has this kind of Gibbs phenomenon. It has a ripple thing going on that this guy doesn't. Okay. And moving on here, this picture is supposed to show how the quality of reconstruction changes as you add more projections. So this is trying to reconstruct that same thing that we saw before using linear interpolation and concentric square sampling. Here, if you just use 16 projections. Here, if you increase to 32. Here, if you increase to 64. And by here, you've increased it to 128. So as you increase the number of projections, as you would expect to get better reconstruction. Okay. So are there any questions? So this nearest neighbor and first order is kind of a naive, or the first thing that hits your mind kind of way of reconstructing. Now there is a formula called the radon inversion formula that has been around again for a very long time. I think almost 100 years that radon developed. And that radon inversion formula results in a technique that's called convolution back projection. And the next thing I like to do is derive that so that you can see how it works. And then after that, I'll briefly talk about the third method of reconstruction. It's called an iterative, and then that wraps up the lecture. So to recap everything, here's the various reconstruction strategies. Okay. So the first one is pretty simple, and as we just talked about, it's either nearest neighbor or it's a first order. This is called zeroth order interpolation. This is first order interpolation. Okay, and the second one is the radon inversion formula, and the third one is iterative techniques. So the advantages of iterative techniques, as you'll see, is that as the iterations go on, the quality of reconstruction improves. So once again, what you could do is, if you've got n projections, you can tentatively reconstruct something using iterative techniques, and then decide kind of whether you want to take more projections. And as you take more projections, the quality progressively improves. Some other techniques, for example, if you think about the interpolation techniques, to begin with, if you just have two projections, you can do the nearest neighbor or first order interpolation. But if you've got four projections, you have to start all over again. As you add more projections, you kind of start from scratch again. So those are not very good for progressive reconstruction. The iterative technique has this advantage that you can progressively reconstruct. Was there any question?
Yeah, just to clarify.
The things we were looking at in the book, we were just basically taking an image and sampling it, and then trying to reconstruct that same image with interpolation, right?
No, we took projections. You started with an image. You took the projections over either 32 angle, 16, 64, etc. Then you took the one-dimensional Fourier transform of the projection. That's right. And then from each of those one-dimensional Fourier transforms, give us samples of the projection along some angle, slapped it on, and then tried to reconstruct the 2D. That's right. Okay, so let me move on to radon inversion formula. Okay. So if we start with this continuous time signal, f sub c of t1 comma t2, which is just the inverse Fourier transform of the fc of omega 1 and omega 2 function, e to the j omega 1 t1, e to the j omega 2 t2, d omega 1 d omega 2. And this is all the omega 1 and omega 2 all going from minus infinity to plus infinity. Okay? And why do I dwell on this Fourier transform thing so much? Because we are, in some sense, by having, each time we take a projection, and it takes the Fourier transform of that one projection, we're getting samples of this guy, right? So it's inevitable to deal with the Fourier domain. In fact, in many medical imaging modalities, the Fourier transform just, without us really, it comes into play automatically. MRI is another modality. When you go in that magnetic tube and they do the samples, etc., all the junk, at the end of the day, they have computed the two-dimensional samples of the Fourier transform of, a slice, let's say this slice across my body, automatically. And the final step before the doctors can look at the pictures is the inverse 2D Fourier transform. So Fourier transform is one of those important. The reason why Fourier transform is so important is that in many applications it occurs naturally. I mean, think about it. MRI. what is it? It's a coil, and you apply a magnetic field to select a plane, and then you apply pulses. None of those things know about Fourier transform, do they? No. I mean, to a physicist, let's say to somebody who's never seen Fourier transform, none of the things I just described have anything to do with Fourier transform. It's a bunch of inductors and coils and magnets and B fields and H fields and atoms spinning and atoms relaxing and pulse patterns. Nothing to do with Fourier transform. But when you're all done, you're sampling, and those guys call it a K-space, you're sampling in the 2D Fourier domain, which means that to get your image back, you got to take an inverse Fourier transform. So the Fourier transform in that sense is very powerful. That also in optics application, in SAR, synthetic aperture radar applications, in many applications, it automatically appears in the scene, and so there's a need to undo it to get the thing you're after. Okay, so here's the radon inversion formula, and I'm sorry, here's the inverse 2D Fourier transform of f sub c, and I'm going to convert this to polar coordinates in order to be able to arrive at the radon inversion formula. And I won't go into all the steps of it, but you can show that I'm going to replace omega 1 and omega 2 with little omega and theta. And so in that case, f sub c of T1 and T2 is given by 1 over 4 pi squared, the integral from 0 to pi of d theta, and then the integral from minus infinity to plus infinity of d omega. And this d omega, in the polar coordinate sense, I'm making theta to be this angle, and omega is kind of the radius going out. Okay? Omega is not the same omega you guys have seen in 123, which is the the angular frequency. Okay, so f sub c, and now I'm going to replace omega 1 and omega 2 with the polar version of it, which is little omega cosine theta, comma little omega sine theta times let's see, e to the j, and now I'm going to replace this omega with this omega 1 T1, omega 2 T2 with the appropriate stuff. So it's e to the j little omega T1 cos theta plus T2 sine theta. And there's one more thing I have to add to this integral in this conversion, and that's absolute value of omega. Okay? So theta is going from 0 to pi, and omega is going from minus infinity to plus infinity. Omega is the radius thing. And staring at this thing, the polar coordinate change was a good thing to do. Why is that? Can anybody say? Because this thing here is what? This expression is nothing but, it's the projection along the angle theta as a function of omega. So I can write this thing as f sub c of T1 comma T2 1 over 4 pi squared. A lot of times people ask me, how did you know you have to convert to polar coordinates? And the always answer is, I didn't figure that out. Somebody else did, and I'm just presenting that. And after a while, when you're busy in this business, you know you have a bag of tricks, and you just keep applying them. So 1 over 4 pi squared, the integral from 0 to pi, the integral from minus infinity to plus infinity. Now it's p theta of omega, and then this thing repeated, e to the j omega T1 cos theta plus T2 sine theta times absolute value of omega, d theta. Okay? And now I'm going to name this integral here, all the way from here to here, I'm going to call that integral I. Okay? Okay, what can we say about I? Well, it seems very much that I is the inverse Fourier transform of the following expression. P theta of omega times absolute value of omega. However, in that Fourier transform, I have to replace t with this expression here. If I just took inverse Fourier transform of p theta omega absolute value of omega, I get something that has t in it. I have a function of one variable t, but I have, because, and that's that variable, so I have to replace whatever that, if I call that t, that variable with t1 cos theta plus t2 sine theta. Okay? So this is, it seems like this thing here is some sort of an inverse Fourier transform. So, but what is the inverse Fourier transform of? What is this expression here? Well, if we, let's just define this g theta of omega to be this guy, p theta of omega times the absolute value of omega. So in that case, what we also say that the inverse Fourier transform of g theta of omega is just little g theta of t. Okay? So what can we say about all these things? Well, having defined all these things, let me rewrite I, and if you can roll up just a little bit so people can see I. Okay, great, thank you. So I can rewrite I, this integral, as the integral from minus infinity to plus infinity of defined p theta of omega times absolute value of omega as g theta of omega times this long exponential e to the j omega t1 cos theta plus t2 sine theta times d omega. So what can we say about this? Well, because the inverse Fourier transform of g theta of omega is g theta of t, so I is just g theta of t, but evaluated for t being t1 cos theta plus t2 sine theta. That's what I is. So in other words, I is g sub theta, just replace the t with t1 cos theta plus t2 sine theta. That's what I is. And now I'm going to come back and plug in the expression I just found for I into this thing here. So fc of t1, t2 is 1 over 4 pi squared, the integral from 0 to pi, of g theta. So let's do that. So plugging back all the way up, you get f sub c of t1 and t2 is 1 over 4 pi squared of integral from 0 to pi of g sub theta t1 cos theta plus t2 sine theta d theta. Okay, so that's a big step. That's a big equation, and let's now interpret and see if it is any useful after that, taking all these symbols and pushing them around. Does it amount to something interesting? I think it does, because why? Because think of what all these things mean. What is g theta? Well, we already know from up here that g theta is the inverse Fourier transform of this capital G theta, and capital G theta is the product of these two guys. So putting all these things together, what does it tell you? It says, start with your projection, p theta of omega. Or rather, start with the p theta of t, your time domain projection. Compute its Fourier transform, boom, right here. Multiply it by this guy, by absolute value of omega. Then take inverse Fourier transform, get g theta of t, and then plug it into this thing. Or you can be a little bit you can go one step further and say, well, instead of, if I'm multiplying these two functions of omega in the frequency domain, what am I doing to them in the time domain? Convolving them, right? This is the Fourier transform of my projection. This is omega, the frequency axis in the continuous time domain, right? So this has an inverse Fourier transform. It's a one-dimensional function of time, t. And this has an inverse Fourier transform. That's the projection we got. Those are the integral that we achieved. Before taking its Fourier transform, it was in the time domain. So get those two time domain signals, convolve them with each other, and that gives us g sub theta of t straight on, and then plug this back here. Okay? That's why it's called convolution back projection. I'm going to convolve the projection I got in time domain with the inverse Fourier transform of this, whatever the thing is. That's the convolution. And then plug it into the integral, and that's called back projection. Okay? So let's write down these steps. So we're recalling that g theta of omega is p theta of omega times absolute value of omega. Okay? So that means g theta of t is k of t convolved with p theta of t, where k of t is just the inverse Fourier transform of this funny function, omega, absolute value of omega. And what is, we can also show mathematically that g theta of t is nothing but the derivative with respect to time of this integral, p theta of tau over t minus tau d tau. Okay? So this convolution with inverse Fourier transform of this guy is nothing but taking the derivative of this thing. So this explains what we mean by convolution back projection. So the steps to take are start with p theta of t, and then convolve with k of t, which is the same as this integral, to get g theta of t, and then step 3, plug g theta of t into this equation, which let's call it star, into star. And again, pictorially, after I compute g theta of t, what does it mean that I plug it into this? Let me draw another picture to kind of clarify that. What is the intuitive meaning of this integral? It's this. I come here, and I have T1 and T2. This is the plane I want to reconstruct my two-dimensional object. This is F. This is where I want to find FC. And after I compute g theta of t is a function of one variable, t, right? It looks something like this. This is g theta of t, right? And what it says is that for each value of t corresponds to a T1, T2 plane. So when t is this value, then it's T1, it corresponds to T1 taking, T2 taking this, and T1 taking that. What that means is whatever value g theta of t takes at this particular value of t, let's call this t naught. At t equals t naught, the height of this function g theta tells me the height of the FC of T1, T2. Is that clear? So if this is g of t and at t naught is taken on g of t naught, then and t corresponds to t1 and t naught corresponds to t1 naught and t2 naught. Here's t naught. This is t2 naught. This point is t1 naught. Then f sub c at t1 naught, comma t2 naught is equal to g of t naught. Is that clear now? So I start with g theta of t, it's been computed at angle theta. Don't forget to label that. It's some sort of a function, and I'm saying the value of that. Oh, sorry. No. No. That's correct. Not quite. Actually, this is not quite correct. So I get this, if I look at this integral, all right, I have to stack up all these g thetas and add them up before I get the FC of T1 and T2. So this is still correct, actually. Technically speaking, this is correct. But it says that this one gives me the value of FC of T1, T2 along these samples. And if I wanted to get all of FC of T1, T2, I just integrate this g theta along different angles, here, until I'm all done. Plug it into this equation so that to do the back projection to get FC. Is that clear? Or did I confuse enough of you? Yeah. Question.
So you essentially you pick a T1 and T2, and then you do add all of them for all the thetas.
Right.
Yeah.
That's correct. So this part of it is, strictly speaking, not quite correct. But yeah, for every value of T1 and T2, I get these g thetas, and I do a one-dimensional integration of it. So this is called, again, convolution back projection. And the convolution part is to get g theta, because g theta is the convolution of, remember, g theta is the convolution of k with p theta. So that's that part. And then the back projection part is just this. So yeah, that's correct. So let me show you some pictures on page 374 of the result of convolution back projection before the lecture is over. All right. So what I have here is that original signal that you saw, comparing right. Okay, so this is the original. Can you zoom in just a little bit to this part? So what it is this is the original signal we started off with. No projections, nothing. Here is if you use the technique we use to reconstruct both of these is the convolution back projection. However, on the left we use polar coordinates. On the left we use concentric squares, and here we use polar coordinates. So you could, I don't know how well it shows up there, but again, the polar coordinate stuff, it has a little bit less resolution than the concentric square one, but this has a little bit more Gibbs phenomenon oscillation kind of going on. But more interesting than either one of these things is to compare. This is using 64 projections. To compare, for example, this guy with concentric square using back projection against concentric squares using, again, this is using 64 projection concentric squares using just linear interpolation versus this one, which is using back projection. So you can get a lot better reconstruction using back projection, convolution back projection, than you would with just simple interpolation. So those are the two things you've got to compare. 64 projections, concentric square, 64 projections, concentric square. And here is one more time, can you zoom out please, showing back projection technique doing 16, 32, 64, and 128 projections. So again, the quality of reconstruction becomes much better as you increase the number of projections. Well, at 128, this is almost indistinguishable, at least by the time it gets to the TV screen from the original one. Okay? Okay, just before we end today's lecture, let me just talk for 1 minute about another technique, because I already advertised it so much, and that's iterative projection, iterative reconstruction, sorry. And the basic idea there is you've got your projections, and you get into this iterative process, and whenever you do iterative reconstruction of anything, one of the biggest dangers is what? Convergence. So the way it works is f sub c of t1 and t2 at iteration k is the answer that you got at iteration k minus 1, which is f sub c of k minus 1 t1 comma t2, plus the sum from I equals 1 to n of lambda i's, which are some sort of a knob that determine the convergence rate. So they determine convergence rate. And what do we normally put here? Usually you put a error term here, right? So the final answer is a combination of the old answer plus some adjustment. And how much you adjust depends on what? Depends upon how correct was your previous answer, how much error it was in the previous answer that you got. And the way you do that is you compute the projections, the actual projections, compute the difference between the actual projections and the computed projection of the previous answer you got. So p sub theta of I of t1 cos theta plus t2 sine theta minus the di of f sub c k minus 1 of t1 comma t2. So let me now explain this thing here. So this thing is actual projections that you've observed. This is the projection operator applied to the previous reconstructions, to the case iteration reconstruction. Okay, so at the kth iteration, I computed some signal that I thought is my answer, and now I apply the projection operator to it to compute. Okay, if that signal was really the answer, what would its projection be along these n angles? And I compute each one of those projections from the actual projection I started off with. Remember, that's the input to my algorithm. And that causes some error. When the error here is very large, that means that my signal f sub c of k1 was off from the real answer, and therefore this term is large, and so this term dominates the final answer, and I tweak the final answer a lot. This term becomes large. On the other hand, as f sub c, as the answer that I'm computing gets closer and closer to the real answer, the difference between these two terms becomes smaller and smaller. Therefore, I perturb the answer that I got in the k minus first iteration less and less, and my signal begins to converge. So this is kind of an error term, right? So let me see if I can show you if there's an example of the iterative reconstruction in Mercer's book. I think it's, unfortunately, I don't see that. And generally speaking, as I said, one problem with iterative techniques is that convergence could be slow. Sometimes the convergence could not be there. So, and sometimes the convergence and the final answer you get depends very much on how good of an initial guess you made. So one possibility would be to use a simple technique like linear interpolation to get a dumb, quick answer as your zeroth iteration, and then improve it by applying the iterative technique. So you can mix and match these techniques as you wish. Okay, that's the end of today's lecture. I'll see you all on Friday.